I think Leroy set up high standards now. I don't think I can make such a funny, nice presentation as Leroy. Very high standards. Congrats, bro. But I will do my best because actually I'm here to talk to you about a nice story. And actually, this is not just a story, but this is our own saga and our own fight against DDoS attack. I don't have time to introduce myself. You already know me. So let's go to the first slide. So our DDoS saga, and we talked about DDoS yesterday a lot, started back on June 2020. I think I have to stand here. When we had the Sunday disruption of our network and we lost everything, all the connectivity in the office, also the VPN users were disconnected. We had not email, not messaging, no Nagios, DNS, transit, nothing. And therefore, no access to internal and external resources. So we became blacked out for several minutes. And then recovery started happening by itself, but in a very slow pace. But then when we looked into that, we saw that the AMS-IX customers and the peering LAN were not affected, which was good. And the transit and BGP sessions from us to the outside world flapped. And after that, the incidents started happening again and again. So it didn't take us much time to understand that it was a DDoS attack. We were victims of a DDoS attack. And when we started looking into the anatomy, what a surprise, it was UTP port, DNS traffic that was hitting us with small to medium-sized packets. The destination IP was one of our public-facing name servers. And then source IP and source UTP port were totally random, of course. And then when we looked better into the graphs, we understood that, OK, wait a second, just a few megabps of traffic that actually hit us. All right, so then here comes the big puzzle to the engineers, right? So if the traffic, if the DDoS attack was just a few megabits, then how the hell we collapsed? Why our network collapsed so easily? First question that came to our mind was that it was maybe a bottleneck on the network somewhere, logical question for every network engineer, or maybe did our name servers collapse simultaneously and then everything freaked out in our network? So as you can see in the graphs, on this graph actually on the left side, is from our monitoring system, and as you can see, the traffic that goes from the routers to the internal network is just a few megabits of traffic. Not even 50 megs. But on the right side, as you can see, this is the CPU utilization of our border out, of the firewalls, of the firewalls that we have to protect us. And as you can see, they match, the timestamps match. OK, that was a very nice clue that we had to help us. And then before I go deeper into the story, I would like to give you a very quick overview of the AMS-IX network, of the office network that we have, which is a very simple network. Just consists of 2 Cisco border routers, ASR 1001 series. We have 2 firewall clusters, and every cluster consists of 2 Palo Alto firewalls, 3050 series in an active passive setup. And in the middle, we have a management layer of Dell switches running the Pluribus operating system in a spine leaf topology configured in a fabric mode. And you have also a farm over there with servers that they run our own services like DNS, HTTP, mail, and so on. So quickly to how the traffic flows into this simple network. Let's take, for example, the DNS traffic in the red color. As you can see, traffic comes from the transit network. It hits the border routers. Initially, the border router does a checkup to see if it is a valid packet from a valid source, and then forwards the packet to the management layer, which then goes into the firewall. Then the firewall does a deeper inspection. It checks further the packet, the payload, if everything is good and valid. If everything is fine, then the firewall sends the traffic to the name server. The name server then creates a response, goes back to the firewall, and then to the outside world. So that's how we handle more or less the traffic. It's a very, very simple setup. But then if we look into the security zones of this traffic and how it's being handled, traffic comes from the transit zones, goes into the untrust zone, as we call it here internally. Then the firewalls pick up the packets, examine the packets, and then they place the packets into the DMZ zone where the servers, like the DNS servers, pick up the traffic and handle it. And then when we were looking deeper into this, setup with engineers in the NOC, we figured out that, OK, the famous rule of the firewalls called UD210, which is the one that handles this type of traffic that I just explained, had this nice button clicked in, which is log at session end. What does that mean? It means two things. First of all, that the firewalls, they do monitor the DMZ traffic, which is a very questionable action. And second of all, they do keep session for this traffic that goes into the DMZ zone. So this actually created a huge, let's say, discussion and not a fight between the network engineering team and the security team, because we wanted to get rid of this rule, or not actually the rule, we wanted to get rid of this action. The security team didn't want, and that started a huge ongoing discussion and further meetings and so on, which ended up nowhere. But in the meantime, we had attacks coming again and again and hitting our network. And the saga continued. But now we knew where to look at. We went back to, in the next attack, we went to the monitoring system, and we saw clearly that the session table of the firewalls was full, and which causes the firewalls to freak out because of this nice button. So, but it was not actually like that. To be honest, it was more of a chain reaction, right? It doesn't take only one action to drop down the network. It takes more things. So in short, we have valid DNS queries coming to our domain. And then the firewalls register those valid queries into the session table, and then they forward the traffic to the name servers. And before the old session expires, because the sessions have an expiration time, but before the expiration time comes, new packets arrive in a fast pace to the firewalls, and then the firewalls register the traffic in the session table. And then the session table becomes full, and the firewall freaks out. And because the firewall freaks out, the LACP connections between the firewalls and the management network, they drop, which means that the OSPF sessions between the firewalls and the routers, the border routers, drop as well, which causes, as you can see, the internal infrastructure losing the default gateway, which are the firewalls. And because the internal infrastructure loses the default gateway, it creates extra syslog messages, and all the applications that we have, the internal applications and the internal systems, they start to freak out. Then they cause extra syslog messages. And that creates a nice loop internally, because these syslog messages are being forwarded via the firewalls, and then they create more sessions to the session tables, and so on and so on. And on top of that, the cherry on the cake was that somebody enabled the NetFlow on the Palo Altos, and everywhere around in the internet, people say that NetFlow implementation on Palo Altos is not that great and creates extra CPU overhead. So we were actually killing ourselves. So first thing that we do was, OK, can somehow mitigate this with the Palo Alto firewalls? Can we do something with the Palo Alto firewalls to protect ourselves? So we opened up the documentations and the instructions from Palo Alto. We found that there's a feature called zone protection that we can use and can help us. And actually, the zone protection is actually helping the firewall against floods that are from SYN, ICMP, ICMPv6, and UDP traffic, and all those type of IP floods. And then we checked into the documentation, the specifications, and according to Palo Alto, the session table has 500,000 of sessions that can register, and it can register up to 50,000 per second. So we went to the configurations, and we put over there, as you can see, the limits, not very lower, but much lower compared to what the firewall can do. So raise your hands if you think that this works. Wow, nobody. You are right, because unfortunately it didn't work, of course. And in the next DDoS attack, we figured it out nicely that, OK, as you can see, again, session table was full. It was UDP traffic. Data plane of the firewall was 100%. The management CPU barely survived. But we were down again. So it didn't work, unfortunately. And then, OK, then the question comes, OK, this solution out of the toolbox. So what was left to us to help us mitigate this? We only had, by that time, a contract with NBIP, with a Nava solution. We talked yesterday about that, with the DDoS protection. But that was something that we never tested, so we didn't know if it works. There was no router configuration on how to use that, and of course, almost no documentation about it. So I had some slides about how it works, so I'll skip them because of time. But most of you know how Navas works. So let's go further, sleeves up, and it's time to work to make this solution work. We split it up in 2 tracks. One was the sysops tracks, where the guys like Miguel actually had actions like to move the public-facing name servers to the cloud, and over there enable the embedded DDoS protection of the cloud provider. But we had also the knock track with the knock actions, which was to build a solution that can put an end to this story and never feel pain again. So the first improvements that we did was to review and fix the Cisco configuration that we had. So we had to make it as simple as possible, so every NOC engineer can execute the required actions in a least amount of time and with accuracy, and can do that during an attack. We had to document all this properly, of course, and we have to correctly test it and then fine-tune it. But then the question is how you test it, right? We talked about yesterday about going to the dark web and then buy some DDoS attacks to your domain. But unfortunately, on the dark web, they don't accept my AMS-IX credit card, my Amex, and I don't want to spend my Bitcoins. So we then went to NBIP and said, if you can, guys, help us launch a DDoS attack against our domain. But by that period, NBIP had a machine, but it was out of production for some maintenance, and they didn't know when this will come back. So this didn't work as well. So there was another solution, which was just to buy a virtual machine from a third-party hosting company, and over there with some tools like HPing3 and so on, launch a DDoS attack against our domain, our network, and then see if it works. But then we faced an unforeseen situation, because actually all the hosting providers that we know and we could think of actually are AMS-IX customers, and they're just one hop away, so the test would not be realistic to us. So we had to find something that is a little bit further away and be more realistic. Then with the help of my friend Miguel, we found a Spanish provider somewhere in Madrid that was like 5 to 6 hops away. And he could help us. He gave us a nice VM with lots of resources, and he could disable also URPF, and that was really good. And then sleeves up, and we started writing a nice script, no more than 300 lines of Python code, that actually could generate DDoS traffic, valid DNS queries, actually. So you can generate valid DNS queries, and then launch these DNS queries against our domain as fast as possible, actually simulating a real DDoS attack. Do you think that works? Correct, it worked! So the DDoS attack worked, but also the preparation and the mitigation that we did all this time worked as well. So over there, we found the first successes that we had during this project. So that was a really, really good thing. It was very motivating to us. We liked it a lot. But then, again, there was a question, okay, can we automate this? Because still, everything is manual by that time, even if it was successful. And then pure NOC guys, they still have to wake up at 3, 4, 5 in the morning just to mitigate an attack of few megabits per second. And by the time you wake up and you go to your laptop to mitigate the attack, it's already too late. The firewalls have already freaked out, and you have to use other solutions to get into the network and mitigate the attack. So we had to find something, had to do something to automate this. So what are we missing to automate this DDoS mitigation? So we have the shield, right? The shield is the Nava solution that we already have a contract and we know how to engage it. So now we are good on that. But we need something, we need a brain, right? We need a brain that can recognize the DDoS attacks and can recognize successfully not only the flow-based DDoS attacks, but multiple types of DDoS attacks. And it can also handle the AS1200 BGP advertisements. And this solution, this brain, needs to stay up and running, regardless if the firewalls or the management network collapse. And of course, needs to be reliable solution, future-proof, and not cost a fortune. And we need to find the brain, and then we need to find the glue as well to glue these parts together. So we found the brain very easily. We just went directly to FastNetMo solution, which is a reliable and automated detection system, according to what they say. It can also detect flow-based attacks, and has a community version and an advanced edition as well. It can support multiple sample technologies, which makes it future-proof in case we change the border routers. It's very automation-friendly and can mitigate attacks based on Go BGP or ExaBGP software. And OK, so we have the brain, we have the shield, and how do we glue those two together, right? So this is the part that we're missing now. We found the glue very quickly, actually, because we decided to use the peering LAN, the AMS-IX peering LAN, where our customers do peering. And why we decided to use the peering LAN? Because the peering LAN is reliable, is stable, and has huge capacity. And we can bypass successfully the management layer. So regardless if the management of the firewalls go down, the peering LAN will never go down. And of course, the IXP prefix of the peering LAN is never advertised. So this is a network that's actually hidden to the rest of the world. And all the components of the peering LAN are monitored 24/7 from QNOC. So we know that this thing will always be there for us. So then the question was to us, OK, what should be the signaling method to handle the BGP advertisements? Multiple approaches were considered during our meetings, like SSH, HTTP API, or BGP, but we decided to opt for BGP with the BIRD software because the NOC team has good experience with BIRD. And there's a lot of internal documentation inside. We can monitor those BGP sessions between the mitigation solution and the border routers 24/7 with Nagios. And the signaling method with established BGP session is super fast. And we can use also BGP communities to do some fine-tuning. So then we started building an automation pipeline, which actually looks like this, but the key components of this automation pipeline is, of course, the FastNetMo community. We use NetFlow for sampling, unfortunately, because of Cisco. We use Python and Jinjan 2 and BIRD. We use internal BGP and BGP communities for fine-tuning, and some Cisco route maps to handle the advertisements on the Cisco. Very quickly, how this works. Sorry for that, but I have to explain. So the Cisco border routers send the samples, the NetFlow samples via the peering LAN to the FastNetMo daemon, which actually, when it detects an attack, it calls a script notify about attack SH, which registers the attacks and then calls a Python script, which actually does a mitigate. This actually script does all the nice stuff. The mitigate script actually configures BIRD accordingly because it knows which prefix is under attack. So it configures BIRD and signals the border routers and say, OK, this prefix is under attack. Please send it to NBIP in order to be scrubbed. And then the scrubbing happens from NBIP, so we get back the clean traffic. We had to use different strategies, however, for IPv4 and IPv6. For IPv4, if a prefix arrives and is tagged with this community, 1200:511, we block the propagation to the transit and peers, but we send the prefix only to NBIP in order to be scrubbed. For IPv6, however, because we have a /48 and we cannot advertise more specific to the internet, we just withdraw the IPv6 prefix from the transit and peers, and we announce it only to Navas. So Navas becomes the temporary provider of IPv6 traffic for us. does it work? We did another exercise internally. We make a maintenance. We went to a maintenance window during the night. We launched again the same attack. We managed to create and send around 2 million packets of IPv4 and 2 million packets of IPv6 DNS traffic to our network to test the solution. And we just did nothing. We were just sitting there, looking the logs, the screens to see if it works, and it worked perfectly. And we actually did some measurements, and we saw that it takes approximately 45 seconds from the time I launched the attack until the time it's completely mitigated. So everything, all the components to kick together and mitigate the attack, it took no more than 45 seconds, which was great success, right? It was less than a minute, which was our threshold, our internal knock threshold. And as I said, we didn't perform anything, just sitting there, eating popcorn and looking at the logs. And unfortunately, the IPv6 attack didn't, it was successful and the mitigation didn't work, but that was due to fastnet mode because it cannot detect IPv6 flow attacks. And some logs from the firewalls that you see the propagation of this IPv4/24 prefix that was under attack. Okay, so that was in a nice exercise, but the question is, does it really work in the real life? So I was going last year to a workshop and I had a layover in Frankfurt, and then I opened my laptop just to see what's happening over there. And during my layover, I saw that during the night, we had like 6 DDoS attacks happening to us. And then I went to the chats and to the logs and saw that nobody from the NOC team was aware of that and not informed. Then I talked to Ronnie, who was the standby engineer during the night. I said, dude, I mean, did you get any call? Everything all right? I saw 6 DDoS attacks happening. Is the infrastructure good? Are we okay? And he said, nobody called me. Nobody noticed it. I had zero notification from anyone about it. You're the first person that tells me about it. Okay, so that means we mitigated successfully 6 times and everything was unnoticed. So you didn't wake up 6 times to mitigate a few megabits of traffic, of DDoS traffic. And that was amazing. That was amazing because it means that we achieved our goal. So actually we became from heroes. So some final automation touches to our solution. We linked it to our monitor system, which is the checkm case. So in the case that we see an attack coming in, we get a nice notification, and the NOC is aware. So it should not be that hidden anymore. We also put a Grafana dashboard so we can see how much traffic is coming to our network. So nice stuff. Some lessons learned regarding this, because it was a bumpy ride, guys. It was not easy, right? It started 2020. It took us quite some time to understand and build a solution. And we had to build everything from scratch, right? As I said, we had 0 by that time. And also what we did, we had to also tweak the NBAP thresholds because we noticed that scrubbing was not engaged on time or maybe not at all. So we had to talk with NBAP to tune the thresholds. We had to do also a lot of NetFlow tuning. Fortunately, please don't use NetFlow if you have anything over there. It's really bad. We also had to adjust our ROAS, our RPKI ROAS. Of course, no max length is required here. And then, okay, one lesson that we learned was that IPv6, okay, although people advocate and they go in public media and conferences and go for IPv6, we see that we are not there yet with IPv6, unfortunately. But the most important lesson learned was that we had to train ourselves, right? So as I said, we had 0 experiences. We had to go and train ourselves how to recognize an attack, how to work with an attack, how to mitigate an attack, how to build tools and solutions against these attacks, and so on. So we learned a lot during this saga. Some future steps, and that's my last slide. We decided to move. We were happy with FastMO, so we decided to go to the advanced version that has been done already. The Cisco ASR routers are crap. We replaced them with Juniper MX204 routers. This is done already. And because of that, we also moved from NetFlow to IPv6, and that's even better. So it improves the reaction time. Some other two things that we want to do and improve is to use a more clever mitigation algorithm. So we can use things like RTBH. For some situations, it's better to do RTBH instead of announcing /24 to the public internet. And we can use tools like BGP FlowSpec for that. And from that, I think, of course, I'm over time, but yeah, that's the end of my presentation. And thank you very much for being with me.